So, chapter 7 is now about rotational motion. We're learning about circular motion, so now we're talking about rotational motion, motion of objects rotating about an axis. So, we need to learn some basic vocabulary first. Angular position, the Greek letter theta. You should be familiar with theta by now from geometry, and if you're in pre-calc, right now, then probably by now you've learned about, or you're maybe learning about theta right now. We are going to grow an angle from the x-axis here this way. So that is in the positive direction then. Our rotation will be positive counterclockwise, as we talked about in the last chapter. So there we go. And then it's measured in radians. The abbreviation for radians is RAD. Looks like rad, but it's not. It's radians. And the distance that we have gone, so that is important that you note that that is a distance, is called the arc length. And we use the letter S for that. Is that true in pre-calc also? Are we using S for arc length? Good. So S is arc length. And then we have this ratio, S divided by R here, is actually going to give us the angle theta, and S equals R theta then would be in radians, not degrees. So that is how we calculate the radians, is S divided by R, the arc length divided by the radius. Notice that there's no way we could come up with degrees in that situation. Okay, we can convert from radians to degrees, but that is not talking about degrees. Okay, that's talking about radians. So you'll want to make sure that if you're dealing with radians on your calculator, you're going to want to make sure that the calculator is actually in radian mode, not degree mode, and vice versa. If you're dealing with degrees, you're going to want to make sure that you're in degree mode and not radian mode. So it can be very disheartening when you find that your answer is wrong when you're in the wrong mode. One full circle in theta radians is 2 pi. So as we go work our way around the circle, the arc length divided by the radius would wind up being 2 pi radians. And 1 radian, your conversion is here. 1 radian is converted to degrees by multiplying by 360 divided by 2 pi radians, since 2 pi radians is the full circle. So that's our conversion right here. And it equals approximately 57.3 degrees, which we can closely approximate to be 60 degrees if we're just sort of doing a close approximation, like ballpark figure. Okay. So hopefully this is pretty similar to what you've seen so far in pre-calc, or what you learned in pre-calc if you already took it. But these are our definitions and conversions for when we're dealing with theta, radians, and degrees. So now we have angular displacement. So just like with linear velocity and linear displacement, we also have angular displacement. So how far we have turned, basically, is what we're talking about. The faster an object moves in a line, the farther it will go in the same amount of time, is with linear situations. So therefore, the faster an object moves around a circle, the farther it will travel around the circle in the same amount of time. And that's with angular displacement. Okay, so we have linear displacement and angular displacement. The correlation there is as you would expect. So we're going to be drawing those comparisons a lot as we go, so that you kind of make that connection between the two. So here we have two pictures. The picture on the left, the particle with a small angular velocity. Okay, so we see this letter right here. That it looks like a kind of a loopy W. That is the Greek letter omega. That's a lowercase omega. Okay, so omega is the letter that we use for angular velocity. So right here, angular velocity is omega. Okay, we use V for linear velocity. We use omega for angular velocity. We also have an angular displacement. The angular displacement is theta. Okay, so we have theta, angular displacement, omega, angular velocity. We also have an angular acceleration, but we haven't seen that yet, so I'm not going to talk about it. So we have an angular displacement theta. So the amount of angular displacement that I go through would be delta theta. And of course, the amount of time it took me to go through that angular displacement would be delta t, same as normal. So delta theta divided by delta t would give me my omega, angular velocity, okay? So this is a direct correlation to linear stuff. Change in position versus change in time. It's exactly what we're talking about here. It's just that we're turning instead of going straight, okay? Or rotating, I should say. All right, so on this picture, the particle with the large angular velocity omega undergoes a large angular displacement each second. So this one, because these time signatures are farther apart, means that we're going around faster. We're rotating faster than this one, which has the time signatures closer together.
It's like chapter 1, section 1.
Exactly. It's the same thing over again, except we're rotating instead of going straight. Okay? The correlation is exactly what you think. All right. So now notice, though, this is uniform circular motion. Okay? So we want to find omega in both of these.
All right. So you figure out theta and you divide it by that many seconds.
Yes. So how much did we turn through?
90 degrees on the first one.
So 90 degrees is not wrong.
But in 5 seconds.
But
Pi over 2.
we want to talk about
It's actually
Pi over 2.
Yeah.
pi over 2. We want to talk about radians, not degrees. That's the tricky part about degrees. You don't know radians very well, right? So we went pi over 2. So omega. Now, this is my standard W right here. I want to make my omegas look more loopy than my standard W, okay? So be careful and make your omegas definitely look different than your regular W's, okay?
Get it confused with weight.
So this is not it here, right? This is my omega equals, now we went pi over 2. I'm doing the one on the left right now. Pi over 2 in how long?
5 seconds.
5 seconds. Okay, so this is pi over 2 radians in 5 seconds. So now we just want to do that math. And this would be like a leave it, change it, flip it, or copy dot flip, whichever way you want to call that. So this would wind up being pi over 10 radians per second. And if you wanted to go to decimal on that, you certainly could, right? So what is the decimal version of this?
0.314.
Radians per second. Okay. Now the other one, I'll change colors so we can tell the difference. And I'm going to move over a little bit. So this would be omega equals, we went pi radians this time. In how long?
5 seconds.
5 seconds. So this would be pi over 5 radians per second, which as a decimal would be what? Basically, we're going twice as fast.
628.
Yeah, 0.628 radians per second. Okay? So that's the idea. That's how you would calculate omega, the angular velocity. All right. So now, much of what we learned from linear motion and kinematics will carry over to circular motion, as I've been trying to drive into your head so far already, right? So, for example, the linear displacement equation here, x sub f equals x sub or minus x sub I equals delta x, and delta x equals v sub x delta t, basically copies itself over and becomes the equation for angular displacement in uniform circular motion. So theta sub f minus theta sub I equals delta theta, and that equals omega delta t, because omega is the angular velocity replacement for linear velocity, okay? And theta is the angular displacement replacement for linear displacement. Okay, that was a hard one to say. So we're going to use omega to mean angular speed and angular velocity. So it actually means both. Okay, and that's kind of a tricky one. So if the direction of rotation is not important, then omega is angular speed. So if we don't really care if it's rotating clockwise or counterclockwise, then we don't really care if we're talking about angular speed or angular velocity. It doesn't really matter, okay? But if the direction of rotation does matter, we care if it's clockwise, we care if it's counterclockwise. Then it matters if we're talking about positive or negative rotation. So then we're going to be talking about velocity, okay? Because it's either one or the other. So in kinematic equations, like what we're looking at up here, omega is always angular velocity. And you're going to need to use a negative value for clockwise rotation, okay? So when we're talking about this guy here, then you're going to need to use a negative value for clockwise rotation. If we're not talking about that equation, then it's angular speed is fine, and you don't have to worry about it, okay? Unless you want to specify which way it's rotating. So another relationship down here at the bottom, we have angular speed, period, and frequency. From the last chapter translates over to this chapter. So now we have omega equals 2 pi radians over capital T, remember, is the period. And because of the period on the denominator, we know that frequency is 1 over the period. So that means we have 2 pi radians times the frequency in the numerator. Okay, so these relationships here also are true, carrying over from the previous chapter.
All on black.
All right, so a small steel ball rolls counterclockwise on the roulette wheel, stationary, 30.0 centimeter diameter. The ball completes exactly 2 revolutions in 1.2 seconds. We want to calculate the ball's angular velocity and then find out the ball's angular position at t equals 2 seconds and assume theta initial is 0. All right. So very straightforward problem, actually.
Yeah.
What do we do?
We need to convert our diameter to radius into meters, right?
Okay. 30 centimeter diameter roulette wheel.
It's going to be 15 centimeters, and then multiply that by 100. So
So 30 centimeters would actually be 0.3 meters. So the radius would actually be
0.015. No. Yeah.
Yeah, half of that. That much. Okay. And then
If it does 2 revolutions, that's what, 4 pi?
Completes 4 pi revolutions in
1.2 seconds.
0.2 seconds.
So we can find the angular velocity with that easily. We just do.
Okay. Angular velocity. So part A, omega equals. Now, we have a formula that involves angular velocity with period and frequency. We want to use one of those. What did they give us? 2 revolutions in 1.2 seconds. What is that?
Frequency.
That's a frequency, okay? So if I go back to right here, omega equals 2 pi radians times the frequency, okay? We can just use that. So we have 2 pi radians times, what's the frequency?
2 over 4 pi over 1.2.
The frequency is 2 revolutions in 1.2 seconds.
We need to convert that to
One
radius.
half of 1.12 seconds.
Remember, revolutions is not a real unit. It just sits there. So it's 2. We can write revolutions if we want to, but it's not a real unit. 2 revolutions in 1.2 seconds. Revolutions doesn't really exist as a unit, though. That's it. You don't have to convert anything, okay? So we can multiply that out. What do we get? That's the 4 pi, by the way, over 1.2.
So I need to put 4 pi instead of 2.
Well, 2 times 2 is 4
Oh,
pi over 1.2.
10.472.
And what are the units now?
It's going to be
Meters a
radians
second.
per second.
It's radians per
Oh,
second.
yeah.
So your omega is radians per second.
If it was linear speed, it would have been.
If it was linear, then it would be something different, but it's not. It's radians per second. Okay, now is this an acceptable answer for us?
Yeah.
Probably go 10.5.
They gave us 1.2 right here.
10.5, yeah.
10.5. Okay, yeah, probably more like 10.5. It looks like they're trying to give us 3 here, though. They gave us 3 here.
But that's in B, so it's in a different question.
Okay. Maybe 10.47. I don't know. Who knows? Okay, B. What is the ball's angular position? So how do I calculate angular position?
That's going to be trying to find the period. So we can use that same equation and just solve for t, right?
Angular
So-
position would be,
Delta theta equals.
that's a delta theta. Remember, position is like delta x, and the corresponding value for us in rotational motion is delta theta. So we need delta theta equals, our formula for that is omega delta t. Remember to keep writing these omegas as a loopy W, not your standard W, because it's not a W at all, it's an omega. Okay, so we have this omega that we just calculated, 10.47, but use your calculator's answer, radians per second. And we have a delta t, don't we?
Yeah, 2 seconds.
2.00 seconds. Now, seconds divided by seconds, those are gone, and we're just left with,
radians.
okay, so we have our answer then.
20.944.
So 20.94 then. Radians. How far is that?
Radians? Well, divide that by 2.
1, 2.
Divide that by 2 pi.
That's like 10 revs.
Well, take 20.94 and divide it by 2 pi. What do you get? That's
6.
approximately 6.
Yeah.
So it went around approximately 3 and a little bit
Yeah, 3 and a little bit.
in 2 seconds. Does that make sense?
That sounds reasonable, too.
Yeah, 3.
From what I know of roulette
Yeah.
wheels.
So yeah, that makes sense. Okay. So that's how you do that problem. Fairly straightforward with the formulas. Okay, the crankshaft in your car engine is turning at 3,000 RPM. What is the shaft's angular speed in radians per second?
So then we need to convert the 3,000 to
Straight up
seconds.
conversion problem, right?
Yeah.
Okay, so we have 3,000 revolutions,
Per minute.
1 minute.
So divide that by 60.
Remember, revolutions are not a real unit.
1 minute is 60 seconds.
So we get rid of minutes, put seconds on the bottom. There are 60 seconds in 1 minute. Revolutions are not a real unit, so we just get rid of that. Minutes are gone. So what does this turn into?
50. So yeah.
50?
Yeah, 3,000.
What?
It's just 50.
Just 50?
Revs a second.
Yeah.
RPM.
No. Oh, seconds inverse.
Okay, we have 50 inverse seconds. What did we just calculate?
Frequency.
This is the frequency. We do not have radians per second. We have a frequency. We have per second. So now what do we do?
Oh, we're looking for angular speed. So that's
Which would be the 2 pi f, right?
Yeah.
Yeah.
Omega equals 2 pi
times the
radians times that.
Yeah.
Good. Omega. Wow, that was this lag. Omega equals 2 pi radians times the frequency, which is what we just calculated, 50 inverse seconds.
314.159. So it's
Ah,
literally pi,
it's-
but
yeah.
just not pi.
So because 2 times 50 is 100, we have 100 times pi. So that is the digits of pi. Move the decimal from the 3.14 over a couple spots, and you have radians per second. Of course, this is nowhere near the correct number of significant digits, but that's the idea. Good?
Yep.
Okay. Now, angular position and angular velocity graphs. So if we have the graph here, the graph of the steel ball and the roulette wheel that we just did, with omega equals 10.5 radians per second. So we have on the horizontal time in seconds and on the vertical theta that the ball is turning through. So we can see that the angular velocity is, because this graph is linear, the angular velocity is constant, okay? Because this is a position versus time
So then that would
graph.
mean it doesn't have any acceleration to it.
That would mean there was no acceleration. The angular velocity was constant, so there is no, what we would say is angular acceleration. Technically, because it was turning in a circle, there is acceleration, but that was centripetal acceleration, not
linear.
not like linear, right? It's not linear because it's going in a circle, but not like linear acceleration, okay? Would be rotational acceleration. So at 1.2 seconds, the ball has completed 2 full revolutions right here. Right here, the ball has completed 1 full revolution, okay? At 2 seconds, the ball has completed more than 3 revolutions, okay? Now, the graph here, we have omega is that value. The omega equals delta theta over delta t graphically. That's the slope of the angular position versus time graph. We can create an angular velocity versus time graph by finding the slope of the corresponding angular position versus time graph. So if we look at the slope here, we can create the angular velocity graph. Okay. And since we already noticed that this is linear here, we know that the angular velocity is constant. So yes, you're tracing out a horizontal line. Our angular velocity is going to be some horizontal line. That's not horizontal at all, but it's supposed to be horizontal, right? So whatever that angular velocity was that we calculated, it's going to be that value right there, okay? And that's going to be horizontal. So that's the idea. So Jake rides his bike home from school. The figure shows the angular position versus time graph for a small rock stuck in the tread of his tire. Draw the rock's angular velocity versus time graph using RPM on the vertical axis. Revolutions per minute on the vertical axis.
And that's still revolutions per minute then, is that right?
What was that?
So the graph is in revolutions per minute, or we have to convert it to revolutions per minute?
So the angular velocity versus time graph will have units revolutions per minute. Okay. So the graph will have time on this axis, and they want RPM on this axis. Okay? Based on what you see here in this graph. So I'm going to give you guys a minute to try to figure out this one, and then we'll come back and talk about it. Here's the answer. The rock. What is happening right here?
It is in, well,
I think it gets stuck. It's just sitting
The rock is just sitting there. Jake's riding along. Boom. Jake runs over the rock, gets stuck in his tire.
No.
We start.
there.
Starts going around the circle, right? Okay, so what was the RPM of the rock at that during that time?
0.
Nothing. So it's down here. Until this moment, what was that moment in time?
30 seconds.
30 seconds? Okay, so I'll mark that 30. Okay, now all of a sudden it's going around and around and around. So we pop up to here, right? How does my graph go from here?
Just straight up.
Straight up.
What do you mean?
Like there's no line.
There's
No, I just boom,
acceleration.
right? It's up there. Okay, so I could draw like a dotted situation here to show that. Okay, now what happens?
So he
He's at-
stays like
There's a
that
constant
until 150
all the
seconds.
way.
Okay, so that's a linear situation, which means I'm going to go in what way on my
You're
velocity?
gonna stay constant.
Horizontal over to where?
150 seconds.
Okay, at 150 seconds, what happens?
It stops.
Jake stops at his house or something.
Jake stops. That
Yeah.
could be. So we drop down to nothing. The rock has stopped moving somehow, right? It could be Jake got to his house and now the bike has stopped moving, or it could be the rock got kicked off the wheel somehow. It just ejected off of the tread and it has stopped moving, right? Something happened where the rock is no longer moving. All right. Now, I labeled my time axis. Did you label the RPM axis?
Yes.
600 RPM.
600 RPM?
False.
I got.
Jake's hauling.
I got
We got to calculate that number.
It's 1200.
1200 RPM?
Yeah.
Holy crap.
I got 600 because so you do the radians over seconds.
Wait, what'd you get?
Well, I didn't calculate it, but I got 2,500 over 120.
What's 2500 divided by 120? It sounds like maybe
I got
200
20. I got 20
somewhere around
at the
200.
start, and then I multiplied it by 60 because it was in revolutions a second.
Let's calculate it.
Okay.
So we got to figure out how do we calculate the RPM? We're going to need this value here, right? Which means this value is actually going to be the what?
The velocity.
The velocity. Well, what is the velocity? How do we calculate the velocity?
Using the graph.
How do we use the graph?
Using
Omega.
the distance over time.
It's the rise over run. It's the distance over time.
Which is-
It's
I
the
got
slope.
500 radians over 50 seconds, which is 10 radians per second.
I need 2 points to calculate the slope. I would have an easy one right there and an easy one right there. Okay. So I need to calculate the slope,
Calculations.
y2 minus y1 over x2 minus x1, basically, right? So this y coordinate minus this y coordinate.
120. Wait. Yeah,
Yeah, 150
because it's
minus
150 minus 30.
The y coordinate,
Oh,
not
the
Y
Y,
coordinate.
it's-
The Y is 2,500.
2500
minus 0.
That's where I went wrong.
minus 0 over the x coordinate,
150 minus 30.
150 minus 30, he said,
So it's 2,500 over 120.
over 120. Now, we get a decimal of that, approximately.
Uh, 200.
Yeah, a little over 200.
No. 20.833.
No, it's definitely not 20.
I did 2,500 over 120 and got 20.8.
Oh, yeah, it is.
Okay, yeah. Okay, 20.8, yeah.
But that's is that revolutions per?
Good. What is this?
Revs a second.
That's
This is radians
per second.
per second.
Radians per second.
Okay.
Oh, and then divide that by 2 pi.
Now we got to turn that into something that we can work with. So this is 20.8 radians per 1 second. Now we want revolutions per minute. So we got to turn this seconds into minutes. Seconds on top, minutes on the bottom. There's 60 seconds in 1 minute. Okay. Now we want to get rid of radians. So radians is going to be on the bottom.
Divide by 2 pi. No, you
Radians to revolutions. Revolutions is a non-real unit, but we can put it on here because that's what we need. How many radians are there in 1 revolution?
2 pi.
2 pi. So there's 2 pi on the bottom and 1 revolution on the top. So now we can multiply that through. Seconds are gone, radians are gone, and I'm left with revolutions per minute.
198.9. So basically 200.
198.9. Call it 199. This is 199 revolutions per minute. Definitely not
600.
600. Definitely not 2,000 or whatever the other one was. But 199 revolutions per minute is reasonable for Jake riding his bike home from school, which we assume is probably like elementary or middle school, right?
Because if he were in high school, he would be driving the car.
If he was in high school, he'd be riding the bus. Okay. So that's the graph. That's the answer. So now relating speed and angular speed. So from what we saw back in chapter 6, the instantaneous speed v and angular speed omega now can be related by the following equation. If we combine a couple of different equations that we already know, v equals omega times the radius.
That's exactly what we just learned.
So remember, omega is units radians per second. If you're given a frequency in revolutions per second, or RPM, revolutions per minute, you need to convert it to an angular speed in radians per second. So this is very important. If your frequency is in revolutions per second or revolutions per minute, you're going to have to convert it to an angular speed. Angular speed is radians per second. So omega needs to be in radians per second first before you can do anything. And that is kind of what the last problem had to have us do. We had to convert the angular speed into a unit that we could work with. Okay? All right. A large wind turbine. You've seen these, right? We see them go by on the train tracks all the time as they're preparing to build somewhere. I don't know if you've noticed, but they're freaking huge. Yeah. The blade itself is 50 meters long.
Is that true?
Yes,
Holy.
they're 50 meters long. And they rotate at 10 RPM. So they go around 10 times per minute. And that is true also. When they're
Really slow.
when they're let go to rotate at the regular operating speed, they rotate at 10 RPM. The next time you drive up to Billings, there's that wind farm now on the way up, right? Between Bridger and the border. You can see it as you're driving north. Those blades are turning. Take out a stopwatch or turn on your timer or whatever and let it run and watch one blade. Watch the road too. It's helpful if somebody else is driving, but I've timed it. And this is true. 10 RPM is about right, okay? And those blades are turning at 50 RPM, 50 meters long, 10 RPM. When we're done with this calculation, you're going to be amazed at what you find out, okay? So what angular speed omega does this correspond to? Basically, how fast are these blades actually turning? And then what is the speed v of the tip of a blade? So like what is the instantaneous linear speed of the tip of that blade? How fast is that going right there? And what is the speed at a point 25 meters from the hub? So right here, okay? Now, will B be moving faster or slower than A?
Faster.
Faster. It has to, okay? Just to keep up. So we already know that. But what is the actual speed is the question. So what do we do?
Well,
It's actually a very straightforward problem.
we already know the radius, and we're given a frequency of 10 RPM.
We're given a frequency of 10 RPM.
We need to change that.
10 revolutions per minute means how long does it take for it to go around one time? If you think about it.
It's going to take 6 seconds.
6 seconds. So that is the period. 6.0 seconds per turn, right?
Mm-hmm.
Okay, so now that we know that, we can calculate the omega. Omega equals, we can use the period, the one with the period in it. So 2 pi radians over the period, which is 6.0 seconds. And we're going to be able to get an answer for that. What is it?
1.047.
So we can call it 1.05 radians per second.
seems about right.
So now that we know that, we can calculate using the formula that we just saw. We can calculate the velocity of point B and the velocity of point A. I don't know why I just drew those arrows. We don't need them. Okay, so velocity of B is omega times the radius. We just calculated this velocity here, or the angular velocity. So we have 1.05 radians per second. The radius is 50 meters. What do we get?
Just a little over 50.
What is the actual answer?
52.35.
52.35, so 52.4 what?
Meters a second?
Meters per second.
Holy smokes. 110
Yeah.
miles an hour.
Convert it to miles per hour, double it, and add a little bit. So that'd be 104, make it 110 miles per hour. Yeah. And
It
then
doesn't seem like they're going that fast.
it doesn't look like it at all.
Could you
But
imagine if you were a bird and you just got one rapid?
well, and so that's why birds, when they don't understand that motion. So when they fly through those wind farms, if they fly through those wind farms, and all of a sudden there's something flying in a perpendicular way to them, they get whacked. They have no chance. They don't understand that there's something coming at them 110 miles an hour. So, yeah, it is a problem. So, VA.
So that's just half.
Omega R, the radius is half of the other one, so it's just going to be half. 1.05 radians per second times 25 meters. The answer is 26.2 meters per second. Yeah, it's amazing how fast those things are going. They're so big that they look like they're moving slow, kind of like a train. Trains are so big they look like they're moving slow when they're actually going quite fast. You don't realize it. Okay, so yeah, it's amazing. And next time you see one of those wind farms, take a look and time those blades. And you will see that the ones that are actually moving, some of them aren't allowed to move fast for one reason or another, but the ones that are free to move are moving at 10 RPM. And they are all 50 meters long.
Of electricity.
And they do generate quite a bit, yeah. All right, last problem here. We're done with the section. Which particle has an angular position 5 pi over 2? Shh.
Yeah, that's pretty easy.
Don't spoil
Yeah, it's a pretty easy one. We know that we start at position 0 right here, and every 90 degrees is pi over 2. So we have pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So we just need that position, and that's right there. So the answer is A.